Welcome to another episode of Dominic Does DIY. So today we're going to take a look at 3 different types of motors that you could possibly use in your projects. One is going to be a standard DC brushed motor, the other is going to be a stepper motor, and the other one is going to be a servo motor. And we're going to look at how each of these is controlled and what the uses are and limitations of each one are. Like, when do you want to use the DC brush motor? When do you want to use the stepper? And when would you want to use a servo? So let's get into this with today's episode. And as always, go ahead and like, subscribe, comment down below, and let's get started. Here we have the 3 motor types. On the left, we have the stepper. In the center here, we have the servo. And on the right, we just have a standard DC brushed motor. The first one we will look at is the standard DC brushed motor. So from my other videos, when I was talking about FETs and motor controls, I was using NMOSs to control the power on and power off, and I had an H-bridge to control bidirectional control. But for this example on the brush motor, I'm just simplifying it, and I'm only going to run the motor in one direction, so I only need one FET to control this. And you can also see through the schematic that I'm not using a FET here, mainly because I don't have a FET. I have a transistor, so I'm using a NPN transistor rather than an NMOS. Specifically, I'm using the 2N2222 transistor. So now the difference between a FET and a transistor real quick. I won't get into too much of the details, but a FET is voltage controlled and a transistor is current controlled. So the basic transistor formulas is the collector current is equal to beta times IB, beta being the gain of the transistor. The base current is going to equal to whatever our input voltage is minus the VBE of the transistor. So in this particular transistor, our VBE is anywhere between 0.6 and 1.2 volts. So I'm just going to go with 0.7 for this calculation. And so our base current is going to be 5 volts because L1 is going to be controlled by our microcontroller. So 5 volts minus the 0.7 volts VBE divided by the 220 ohm resistor into the base, give us a base current about 20 milliamps. And with that base current, we can take a look at our gains over here. We'll pretty much saturate whatever we need to do, because this little motor doesn't really pull a lot of current. Might pull 50 milliamps. I'm not too concerned about it, but basically with a 20 milliamp base current, we'll be able to fully saturate the transistor and be able to drive this motor 100% without any drawbacks. So in my prior video with the 1 megahertz PWM from Arduino, I'm basically using that same code in order to output a 50 hertz signal that I'm then going to PWM to the DC brush motor. So same basic concept that was going on with that video. I'm just reusing the code here in order to move the DC brush motor at different speeds. So let's take a look at this on the scope. So here we can see the output of that PWM. We can see it's just going increasing and decreasing. You'll notice that I don't go all the way to 0. It is because if I go less than that, there's not enough current in the PWM to actually spin the brush motor. So let's take a look at the actual motor and see what's happening there. So before I plug it in, you can see the resistor and the transistor right there. And so there's my DC brush motor. I got the piece of tape on it because I don't have a fan or something to let it spin. So it's my only real indicator of what is happening with this system. You can kind of see with the LED, because it is inverse to what the motor is going to be doing. So you can kind of see how it went off and then flashing. That's the opposite of what the motor will be doing. But let's turn this thing on and then spin the motor. So I went ahead and connected up the motor. And now you can kind of see I've got a propeller going. So what I'm going to do is and you can kind of see it slowing down, but I'm going to put my finger here and you can hear the frequency as it starts getting faster. You should be able to hear the frequency pick up and the frequency lower as the speed lowers. Why would we want to use a DC brush motor? One, we want to continually spin something like a fan, tires, propeller, something just continually spinning. Two, we want some RPM torque control that we can get via PWM. Three, though, this DC brush motor, it is not very accurate or precise when you're talking about positioning. This thing, the DC brush motor is good for, in this instance, as just basically spinning something in a circle. So let's go ahead and take a look at the next one, which is a servo. So the servo, for the example I'm going to use on this one, it is just one of these Arduino micro server 9Gs. So with these servers, the way that we have to operate the PWM here is we actually won't be using a huge portion of the PWM. You can see down here at the bottom, one, we need a 50 hertz signal, right, a 20 millisecond period. But then within this 20 millisecond period, we have to have a 1 to 2 millisecond duty cycle to actually tell the servo in which position do we want to go. And you can see over here, they basically have three settings, the far left, the middle, and the far right position. And we can see that they describe it as like a 0, a minus 90, and a positive 90. So when we're looking at those values, it says that the minus 90 position is going to be a 1 millisecond pulse. The 0 position is going to be a 1.5 millisecond pulse. And the positive 90 position is going to be a 2 millisecond pulse. This was the calculator that I was using on the prior video with the Arduino 1 megahertz PWM. And so on that one, we were actually just using a prescaler of 1. So if we tried to do the same thing and just use a prescaler of 1, our 16-bit timer can only get up to a maximum of 65,000. But with a prescaler of 1, in order for us to receive this 20 millisecond pulse, we would have to be able to set that ICR value to 320,000. So that's not possible with a 16-bit timer. So what we're going to do instead is we're just going to change our prescaler. We're going to go down to 64. And now that puts our ICR at a value of 5,000, which is completely capable of doing. Now we need to figure out, what does our OCR value have to be? We know what our ICR is. So we got our period of 20 milliseconds. Now we need to know, what is our OCR value for these different positions. So we can see here with a duty cycle of about 8%, we have the time of 1.5 milliseconds. So that gives us an OCR of 375. If we go to a 5% duty cycle, that gives us an on time of 1 millisecond, and that OCR is 250. And then same thing, if we take this up and go to a duty cycle of about 10%, that gives us a 2 millisecond pulse and an OCR of 500. So you can see here, I've defined a few things. I set my ICR PWM frequency to 5,000 for the ICR value. I've also gone here and I've defined the 0, minus 90, and positive 90 position, except I've called this 0, 90, and 180 for the degree. But it's set to the 250, 375, and 500. You can also see in my loop, I have set the TCC R1B register. I have set the CS10 and the CS11 bit because that gives us our prescaler of 64 that we were looking for. And then all I'm doing inside the code is I am basically going to set the angle to 90, wait a second, set it to 0, wait a second, and set it to 180, and wait a second. And then I'm just going to loop like that forever, moving the servo into different positions. So let's take a look and see what this looks like on the scope. So the first thing you can see here is the frequency is 50 hertz, just like we wanted. And you can also see the milliseconds, even though it's flipping pretty quick. It goes between 1 millisecond, 2 milliseconds, 1.5 milliseconds. So you can see we're also getting the pulse widths that we're looking for. So you can see here, the servo is going to those three different angles, 0, 90 degrees, and 180. But if you notice, looking down right on top of it, you can tell that this thing is not actually going to a 0 position, a 90 position, and a 180 position. It's because the timing on it is not that accurate. So if you looked at the data sheet, if you remember, it said approximately 1 millisecond, approximately 1.5 milliseconds, approximately 2 milliseconds. And so because of that, we're not getting the true full spectrum from 0, 90, and then 180. I could go in there and mess with the duty cycle though, and fine tune it to get the 0, the 90, and the 180 if I wanted to. So we're going to go ahead and take a look now at the stepper motor. The stepper motor is used for very precise angle and rotation that's very repeatable, because every single step is a very specific angle of degree of motion. So we're using the 28BYJ48 5-volt stepper motor. You can see the speed variation ratio of 1/64. So this thing is a motor with a gearbox. And so that motor and a gearbox, it takes 32 revolutions per tick. So in addition to 32 revolutions per tick, well, then we've also got a speed variation ratio of 1/64. So our total steps per revolution of the entire system is going to be 2048. Basically 32 revolutions per tick, and there's 64 ticks per complete revolution. So that gives us a whole total of 2048 steps in order to achieve one full 360-degree rotation. And the frequency that we can run this at is 100 hertz. I'm going to be running a little bit faster than that. So how is it that we can run the stepper motor? So the stepper motor actually uses some Darlington transistors. There's a stepper motor adjustment board. And so it uses this ULN 2003 board. It comes in every Arduino pack. But basically it's taking in those inputs and then allowing you to drive the motor outputs. As you see right in this area here, the stepper motor is a series of coils. And so we got to pull current through those coils in a certain rotation, in a certain order, in order to get the motor to spin. And so we don't want to drive those with the Arduino itself because of the current draw that's required in order to spin those motors. So all we're doing is going through this Darlington transistor array. And so this way we can still trigger the motor coil, but we can use a secondary power supply. It's basically like setting up a bunch of MOSFETs to be able to control the relay that's going on. So inside the code, what do I have? I basically have these defines. I've got my output to each of the coils for operation, my N1, 2, 3, and 4. I define my steps per revolution at 2048. And then I also have a clockwise and counterclockwise bit defined. That way I can control which direction. Because unlike the prior one that I didn't want to set up an H-bridge for the brush motor, I can actually do this in software. So let's see what we actually have to do. So of course there's always the stepper.h file that you can use for easy mode, and it's got all of it built into it for you. For other functionality, I really don't know what it does, but this is a stepper motor, so I just need to be able to step. And so the function I've got is just stepper. It takes in how many steps do you want and the direction. And this is where the clockwise, counterclockwise comes in. But basically all I'm doing is for however many steps I want to go, I check the phase. I call it phase because these are the phases of the motor that we're going on. Phase 1, 2, 3, and 4. There's only 4 phases that I can choose from, 4 parts of the motor. And so basically all I got to do is, depending on which phase I'm on, turn off the ones that are not that phase and turn on the one that is. And so as I'm just going around, right, it goes in the order and the direction of the phases in 1, 2, 3, and 4 as it goes around in a circle. And so I just do the same thing. I turn them off, but you can see that in each case, I'm turning on high, the next one in line. So case 0, I'm turning on in 1. Case 1, I'm turning on in 2. Case 2, I'm turning on in 3. Case 3, I'm turning on in 4. And then basically because of the phase thing, I'm just going to cycle through those no matter how many steps I got. Because remember, I've got the direction, so which direction do I want to go? After I do my first rotation, after I turn on my first motor phase, then what I do, I check the direction. If I'm going into a counterclockwise direction, go ahead and increase the phase. And if the phase gets over 3, then just go ahead and reset it to 0. So I can just loop through these 4 phases. And if it's going in the opposite direction, do the same thing, except subtract the phase. And if I get below 0, then go ahead and reroute me to phase 3, right? So I can go into a constant circle. And I went ahead and put a delay. This is the 100 hertz, right? 1 over 100 is 50 milliseconds. So this is the proper speed for us to be pulsating this stepper motor. And that is pretty much it. That is all you need to do in order to turn the motor counterclockwise or clockwise. You can see in the setup, I basically just set the pin modes as outputs, default them all to low. And then down here, I go ahead and set phase equal to 0. And then I run the stepper 4 times. This is just to get a baseline, because whenever I boot up, I don't technically know what phase the motor's in. So if I just try to go immediately, then let's say the motor is in position 3, but I start out in position 1, I'm going to lose those first 2 ticks, right? So there's only 4 phases. I just run 4 ticks, and then that'll always put me into the proper phase at the end of the day. So for the sake of the video, I went ahead and turned this delay from 50 milliseconds for the 100 hertz frequency down to 5 milliseconds in order to make the demonstration a little shorter and able to be seen. At 50 milliseconds per click, it takes quite a bit of time. So you can see in the code, all I've got going on is I'm going to send the stepper and I'm going to let it step forward 360 degrees in the clockwise position. And then I'm going to go reverse. Let's do 1024. Right, so it'll go 1 full rotation, 360 clockwise, and then it'll do a 180 counterclockwise, and then it'll just keep repeating that over and over again. So let's go ahead and program this and see how it looks. So you can see here, it's going counterclockwise, 180 degrees, and then it shifted to clockwise direction, and it'll spin for 360 degrees. So that's the DC brush motor, the servo motor, and the stepper motor. So as a review, the DC brush motor, this is just when you want to continually spin something. You want to have good RPM torque control via PWM, and it's not very accurate or precise for positioning. The servo motor, however, it can give you a quick angle position set points, like 15 degrees or 45 degrees. It's not very precise, at least this one isn't, due to the way that you tell it, right? That approximate 1 millisecond, approximate 1.5 millisecond, approximate 2 millisecond is not very accurate. It does require some fine tuning to get the exact angle that you're looking for, and it's probably not repeatable for a precise angle across different programs, right? Like on this one, you might find that 27 clicks give you what you want, right? And then on the next one, it might be 35, and that's just coming from you're not changing a program, just you making a second item using the same servo. So you can have some variation in the servo itself. But it's good for any general angle application where if you're not really too concerned about it, you can use it, right? And finally, the stepper. So the stepper is very precise. Each step equals a very specific degree. An exact count of angles will give you 360 degrees. It's slower due to the constant stepping that has to be done, but it's very repeatable with extreme accuracy. Things like CNC machines, 3D printers, things that need to be in a very specific position before they actually perform some sort of action. So based on what your project is, sometimes you want a brush motor, sometimes you want a servo, and sometimes you want a stepper. So depending on what you're doing, just think about the 3 that you've got, and these are the 3 ways that you can control it. So until next time, keep doing stuff and playing around with electronics.